All right, we are back with day 2 of sequences, and we only have 2 examples, but they're kind of big ones. So, all right, this problem says the third and sixth terms of a sequence are 48 and 6, respectively. Find an explicit and recursive formula for the sequence if it is arithmetic. Find one if it is geometric. All right, let's start by writing down what we know. We are told that the third, a 3 and 6th terms are 48 and 6th respectively in that order. So that means the third term is 48 and the 6th term is 6. Now we are not told if this is an arithmetic or geometric sequence. In fact, we are told that we need to figure it out in both cases. So let's start with the arithmetic because that's the easier of the two. All right, so this is assuming it is arithmetic. Now, in order to do this problem, where we know the third term and the sixth term, a4, a5, a6, we are going to need to figure out, we have a3 and a6, we need to figure out what that common difference is. So one way to do this, a3 to a4, so that's plus 1 common difference. We would have plus another and plus another. One way to do this would be to take that sixth term, a6, which is 6, subtract from it a6 minus a3, our third term, 48, and I would get negative 42. I would get negative 42. Okay, and if we go back to what I was doing earlier, sorry, I wasn't really explaining myself very well. So the difference between our third term and our sixth term is negative 42. Well, it took us 3 common differences to get there. So in order to figure out what one common difference is, I'm going to divide negative 42 by 3. That means our common difference D would be negative 14. Now, maybe you're like, I don't believe you, Miss Wissing. One way you could check would be pretty easy, kind of annoying, but you could do it. We could take 48, subtract 14, then subtract 14 again, then subtract 14 again, and you should get to 6. All right, now that wasn't actually the question, unfortunately. That's just going to help us get there. All right, sorry, rearranged a little bit. So here's what we know as a reminder. We are given, again, our third term. Oops, why are you not doing this? We are given our third term and our sixth term. We just figured out the common difference, assuming that this is an arithmetic sequence, and they want us to find both the explicit and the recursive formulas. I'm going to start with my recursive because that's a lot easier. In fact, we don't really need anything right now to find our recursive. So any term a sub n is going to be equal to the previous term, a sub n minus 1, plus the common difference, in this case, minus 14. And honestly, that's it. That is the recursive definition if this were an arithmetic sequence. Okay, lovely. What about our explicit definition? Explicit. Here's what I remember. An explicitly defined arithmetic sequence is going to be equal to our first term plus n minus 1 times d. Now, we already have, if I look through this, we don't need n because that's going to be a variable. I don't need a sub n. That is also a variable. I have d, so the only thing I need to figure out is my first term. And there's a lot of different ways you could do this. We could either go from our a3 and find a2 and a1 by adding 14 and adding 14. Or if we want, we could take a3 and plug in a1 as a variable. This would then be 3 minus, oh my, hold on. Sorry, I did a really bad job there. Let me try that again. If I took a3, okay, a3, which we know is 48, is equal to our first term, a1, that's going to be a variable, plus 3 minus 1, times our common difference of a negative 14. And then what I would technically do, oh, that's supposed to be a different color. What I would technically do is solve this. So 3 minus 1 is 2. 2 times a negative 14 is a negative 28. I would add 48 plus 28 to get 60. 76 is equal to our first term. All right, that's lovely because now we can write our explicit definition. Any term, actually, hold on. All right, I'm going to go to my explicit definition here. So any term a sub n is equal to a1, we just figured that out to be 76, plus n minus 1 times our common difference of a negative 14. And again, we're on our Straight and Pre-Calc. We don't keep things like this. We are much, much smarter. So once we distribute and simplify, we should get a sub n is equal to, pause the video if you want to really quick, just make sure you can do it, but 90 minus 14n. So these are our two definitions if this were in arithmetic. Here's how we would define this one recursively. Here's how we would define this explicitly. However, we don't actually know that this was an arithmetic sequence, so we need to do the same idea for our geometric. So B asked us to do the same thing if this were geometric. Ooh, interesting. So we know, I'm going to take that, we know our third term is 48 and our sixth term is 6. In order to find our R, our common ratio, we need to do a little more work. We know that a geometric sequence is going to look like this. A sub n is equal to a sub 1 times r to the n minus 1 power. But in order to kind of help ourselves find r, we can do one of two things. We are going to solve a system of equations is actually what we're going to do. And I'm going to just show you what I think is the, well, okay, whatever. Okay, let's take these values that were given, our third term and our sixth term, and write them like this. So a sub 3, in this case, is 48. And that's equal to a sub 1 times r to the, well, it's our third term, so 3 minus 1. Or, I'm going to make that a little nicer, 48 is equal to a sub 1 times r squared. And we're going to take our sixth term, a sub 6 is equal to 6, we know it's 6, and that would be a sub 1 times r to the 6 minus 1, or again, making this look a little nicer, 6 is equal to a sub 1 times r to the 5th power. We need to now solve a system of equations using these two equations. And the two main ways we can solve a system, so solve a system would be, oops. Okay, we could use substitution. Okay, hold on. All right, you could use substitution. You could solve for a1 in one of these equations and then substitute it in to the other and solve. I'm not going to use that method actually. I want to use a different method because I think it's the one that we probably avoid more. The other one we could do is elimination. I know we've done a problem very similar to this, but I think it was a long, long time ago. So I have 6 is equal to a sub 1 times r to the 5th, and I have 48 is equal to a sub 1 times r squared. I want to get rid of one of these two variables, either a1 or r, and it's going to be a lot easier to get rid of a1. How am I going to do this? Well, I am going to use division. How do I know division? Because I'm multiplying here. I want to get rid of it. I want to cancel it out. So I'm going to take a1 times r to the 5th and divide it by a1 times r squared. Notice I'm taking the right side of these equations. So that's going to be equal to, well, I'm going to take the left sides of these equations. So 6 over 48. This method is called elimination. Why? Because we can now eliminate our a1s, and we can simplify this here. So I really have r cubed is equal to 6 over 48 is really 1/8. And now I need to find the cubed root. So technically, I'm doing the cubed root of both sides, cubed root of 1/8, which is the same as the cubed root of 1 over the cubed root of 8, which is nice because that is 1/2. Da-da-da! I have now found my r. I'll pause and make this nice. All right, so the big takeaway here is now we have found our common ratio, r of 1/2. Now maybe you're thinking, Miss Wissing, I figured that out already because I just figured out, well, the difference between 48 and 6 would be, I'm blanking. It's 42 if I subtract, but 48 divided by 6 is 8, right? 8, and then 8 divided, okay, never mind. It's been a long day. We're just going to ignore that, and you can just be like, I found it some other way, and that's okay. Great. Okay. That's besides the point. We now have to write our explicit and our recursive definitions. Again, recursive is always a lot easier because this is just any term is equal to the previous term, a sub n minus 1 times that common difference of 1/2. Okay. In our explicit, we need to find that first term. I'm actually going to do finding our first term by multiplying our third term by 2 and 2 again. So I'm going to take a 3, which was 48. I'm going to kind of go backwards, so times 2 and times another 2 to get my first term, which would be, pause the video if you want, 192. That would mean our explicit definition is equal to 192 times the common ratio, which is 1/2 to the n minus 1. Sorry that this is kind of all over the place, but hopefully you're following along. Otherwise, just ask. I would be happy to go through it again. All right, so we've got our explicit, we've got our recursive definitions if this were a geometric sequence, and that is this problem. Last thing in this section is finding the limit of a sequence. So let a sub n, oh, I don't want that color. Let this a sub n be a sequence. Basically, I'm just saying, take any sequence. Then, the limit as n approaches infinity, as the number of terms goes to infinity, of this sequence, a sub n, can do one of two things. This limit can do one of two things. It can either converge or diverge. So I'm going to talk about, well, I'll give you these definitions first. Can do one of two things. If the limit as n approaches infinity of this sequence, a sub n, is actually equal to some number L, then we would say, then the sequence converges, meaning gets to a value. Converges. And if it doesn't do that, all right, if the limit as n, oops, that's really bad, as n approaches infinity of this sequence, if it doesn't come to just some number, if it actually goes to either positive or negative infinity, which again, therefore, does not exist, then we say the sequence diverges. The sequence diverges. All right, how do we decide if it converges or diverges? Well, good news, It's pretty much the same rules from before. Oh, I don't want that. Sorry. Okay. Pretty much the same rules of as before. And so we're going to think about our rational function. Oh, that looks bad. Think about our rational function rules. So remember, rational function is a function where we have some numerator and some denominator. Let's say the numerator has a degree of n, the denominator has a degree of m. So there were three options here. Either n was less than m, and if that was true, the limit was 0. This would be converges. The second option was that n was equal to m. If that was true, our limit was the leading coefficients. Leading coefficients. And, oops, I wasn't going to write the whole word, but okay. Leading coefficients, this again would be a converging sequence. And last but not least, 3, if n was greater than m, in this case, it's either positive or negative infinity, which means that the limit does not exist. And this right here is the case where we are diverging. We are a divergent sequence. So let's look at one quick example. We need to decide whether the sequence converges or diverges. We are given the following sequence: 2, 1, 2/3, 1/2, 2/5, etc. Now notice, they give us the definition of this sequence. This is our term 1, A1. This is, oops, term 2, A2, etc. And this is, oops, term number n, A sub n. This is an explicit definition. Also, we notice it doesn't have that same model of our arithmetic and geometric. That's okay. Not every sequence is going to be arithmetic or geometric. So if we consider the limit as n approaches infinity of the function 2 over n, well, n in this case is really just the variable. So this would be a first degree. This would be a 0 degree, so we could really write it as 2 times n to the 0 power, right? This is n to the first power. So we have our numerator has a lower degree, n is less than m than our denominator. And I'm sorry, this is kind of confusing, I realize, because this n is the degree, not this n. But our numerator has a smaller degree than our denominator, which means this will approach 0, and this sequence will converge, meaning it basically just goes to 0. And that's it. Good luck on your homework. Please let me know if you need help, and I will talk to you soon.